Hello everyone. In the last lecture, we had seen seismic reflection methods. Right. In the last few lectures, we are looking into seismic methods of investigation or exploration. Under that, we had seen broadly how seismic survey is carried out on land as well as on sea. Then we had a look into seismic refraction methods. Then in the last few lectures, we had seen what are seismic reflection methods. Then one another method which is of great interest, especially for engineering purpose, to understand the nature of the subsurface for major engineering constructions, which is known as multi-channel analysis of surface waves, which is popularly called as MASW or MASW, multi-channel analysis of surface waves. Let us go back to what we had seen in the beginning of seismic methods. I showed you different types of seismic waves, right, which are Rayleigh waves, Love waves, then primary waves, secondary waves. The methods which we have seen until now, that is the seismic refraction and reflection methods, makes use of body waves which are primary and secondary waves, whereas multi-channel analysis of seismic waves make use of surface waves which are Rayleigh waves and Love waves. What are Rayleigh waves? We had seen already, but anyhow for our understanding I have put some nice animation thanks to this person, right. Here you can see Rayleigh waves are getting propagated in the form of an elliptical motion, right. So, this is how the wave is getting propagated, right. And this is resulting into a kind of rolling motion at the surface of the earth. So, during earthquakes, surface waves, especially the Rayleigh waves, cause highest amount of destruction, right. As you can see in this animation, you see a kind of rolling wave. That means the ground surface will go up and down due to the propagation of the Rayleigh waves, right. And then what is Love waves? Love waves are very different, right. In the case of Rayleigh waves, if you look at this particular pixel, it moves up and down it is moving like this, right. This is the actual direction of movement, right, as indicated by these blue arrows. Whereas in the case of Love waves, look at this black square, it moves horizontally, right, and the direction of particle movement is shown by this diagram, by this arrow. That means this particle moves to the left and right of the direction of propagation of the Love waves. So, Love waves are traveling along this direction, right, whereas the particle is vibrating in a horizontal fashion perpendicular to the direction of propagation. This is what is known as Love waves. If you look at the characteristics of all these waves, right, primary waves is actually very fast. We had seen already, right. Primary waves are moving through the interior of the earth. They are thus called as body waves. They are the fastest. Then we have secondary waves. Secondary waves are also body waves which are relatively slower to the primary waves. Almost half to 1/3 will be the velocity of the secondary waves. Then we have seen the surface waves. Surface waves are much slower, right, much slower than the secondary waves which are Rayleigh waves. Love waves are further the slowest, much further slower than the Rayleigh waves. So, these are the some broad characteristics of seismic waves which we have seen already. Right? Then what is the theory behind multi-channel analysis of surface waves? Actually, long time ago, right, we know conventional seismic approaches, right, which is the seismic reflection or refraction survey, right. We carried out that to understand the nature of rocks present at greater depths. It can be also used for shallow investigation. That means from few tens to few hundreds of meters we are able to investigate. Hope you can recollect some of the case studies we had seen under seismic reflection up to 4 kilometers, sometimes up to 40 kilometers. For that we made use of conventional seismic methods, especially the refraction and reflection methods. Right. Here seismic signals during these surveys consist of wavelets in high frequency, almost equivalent to 50 hertz, right. That is the kind of signal we had used in conventional seismic investigations, right. Actually, in conventional seismic surveys, surface waves are a nuisance for us, right. So, usually we strategically plan our survey, right. The offset, that is the distance between the source and the geophones, are decided in such a way to minimize the surface waves. That is what we were doing some time ago, maybe before 90s, right, or even today, right. For the conventional seismic survey, surface waves are a noise, right. In fact, out of the seismic energy that we create artificially, right, in an active method, out of the energy we have created, nearly 2/3 of that is actually surface waves. So, they are really dominating, but in conventional seismic survey, we would like to suppress that, right. So, that primary waves, we are going to make use of primary waves. So, our interest is to suppress the surface waves so that we do not have much of a noise in studying the primary waves, right. That is how we have been making use of seismic methods. However, sometime during 1990, we have started making use of the surface waves also, right. The multi-channel analysis of surface waves have developed sometime during mid 90s, right, with the help of analyzing the surface waves which are of much shorter or lower frequency, whereas seismic refraction and reflection, they are at a frequency of around 50 and above, whereas the surface waves are usually of lesser frequency, around 1 to 30 hertz. So, previously these waves were considered as a noise or nuisance in conventional seismic survey, which has become a boon today, right. Most of the investigation, especially shallow investigation for engineering purpose, is being carried out by multi-channel analysis of only surface waves. But we are able to understand with greater detail up to shallow depth. That means the conventional methods we can go up to even few kilometers, whereas multi-channel analysis of surface waves, we are able to understand up to few tens of meters, but in greater detail. We are able to understand how the surface waves got dispersed when it begins to travel below the surface, and we are also able to understand the velocity of the shock waves, how the velocity of the shock waves varied below the surface. All these things we are able to today carry out thanks to this technique, that is multi-channel analysis of surface waves, right. Let us go little bit deeper into the surface waves. Actually, there are two types of surface waves as we had seen in the beginning. One is the Rayleigh waves and the other one is the Love waves. But Love waves are very slow. The velocity, understanding the velocity of Love waves are also little bit complex. Rayleigh waves on the other hand are actually following certain specific norms. That means velocity formula for Rayleigh waves is very simple, and because Rayleigh waves are dispersive, that is what that technique only we are making use of in multi-channel analysis of surface waves. So, the method depend on very much on the Rayleigh waves. I told you already, Rayleigh waves are much slower than the body waves, which are the primary and secondary. Primary is the fastest, little slower is secondary. Rayleigh waves are much slower than the secondary body waves. Surface waves are dispersive in nature. That is what we make use of in MASWA, right? What do we mean by dispersive? Different frequencies of surface waves travel in different velocity. That means the shock waves are of different frequencies, and these waves are also traveling in different velocities. Though the shock has been generated by the source at a particular place, the shocks are traveling in different frequencies and also in different velocities. We know very well these three are very much related, right? Velocity divided by frequency is going to be the wavelength. So, when we say the shocks are traveling in different frequencies, when the frequency changes, the velocity also is going to change. That means the shock generated travel through the formation in different velocities or wavelengths or frequencies, right? What is frequency and the dispersion, which can be very easily understood from light. When the light passes meets the glass prism, it gets dispersed, as you see in this nice animation, right? They are of different frequencies and wavelength. Right? Same thing happens below the surface of the earth, layered earth. When the seismic surface waves meet different interfaces or discontinuities, they get dispersed. That is what we are going to make use of in multi-channel analysis, right? And this is what we refer as frequency. Frequency is the occurrence per unit time. So, frequency, velocity and wavelength are related as per this equation. In the case of surface waves, the waves are traveling in different velocities in different frequencies, right? Whereas, the methods we had seen until now, that is the seismic refraction and seismic reflection methods, they are making use of primary and secondary waves, right? Compressional and shear waves, they are certainly non-dispersive, especially in a elastic formation, right, below the surface of the earth. They are completely non-dispersive. In other words, the velocity of propagation is independent of frequency, right? Velocity of propagation is independent of the frequency. So, that is what happens in the case of body waves. We use body waves for carrying out seismic reflection and refraction survey. We are going to make use of Rayleigh waves for conducting multi-channel analysis of surface waves, right? That is what we are going to see in this lecture, right? What are all the sources that we can use to carry out multi-channel analysis of surface waves? The sources are the same, right? We can make use of hammer or weight dropping method or vibratory, explosives, and also use of guns, which means literally there is no difference. Whatever sources we had used to conduct seismic reflection or refraction survey, the same sources can also be used here. Another advantage of multi-channel analysis is here we can also make use of passive sources, right, which are known as micro tremor energy. However, we should bear in mind we don't have any control, right, when we use passive sources, which is sometimes a disadvantage. The advantage is there is no need to energize the ground by these methods, right. How can we get micro tremor energy? Maybe due to geologic reasons, right. Earth is always under some disturbance, especially in certain zones, at least along the plate boundaries. And we can also make use of the human induced noise. In urban environment, we create a lot of vibration. People are walking and vehicles are moving. We are able to feel the vibration of a heavy truck passes adjacent to us, right. We can even make use of this energy. So, that is one of the advantage. That means we can use either active source or the passive source, right. And here usually when you are dependent on passive sources, high frequencies are absorbed, right, whereas low frequencies from especially from greater depths are mostly received during the survey, right. What I want to say is low frequencies emanating from greater depths we many times receive, right, and the high frequency ones are absorbed. So, these things we should bear in mind when we are using passive sources. So, as you can see in the picture above, in a survey carried out by us recently, we are using what method? What method is this? We are using a hammer, a blow is given to a steel plate, right, and the hammer is also attached to a cable. So, that means the time at which the hammer hits the iron plate on the ground, a signal is sent to the recording unit through this cable. Okay. So, what are all the different sources? Here you can see we are giving a simple hammer blow. This itself can generate large amount of signal. On the right hand side table, you can have a look into approximate depth of investigation, right. What is the depth of investigation? What can be the source we can make use of, right. Suppose if you use a sledgehammer, this is a nearly 10 kilograms. So, we can investigate very easily up to 30 meters by this method of source, right. That means what we did, we just gave a hammer blow with a 10 kilogram sledgehammer. We are able to investigate up to this much of depth. Suppose if you want to investigate greater depth, then we can go for weight dropping method. If you want to investigate much greater depths, as I told you here, low frequency passive signals will be very, very helpful. So, with regard to the sources, there is no difference from that of what we used under seismic reflection and seismic refraction method. But one additional advantage in MASWA is we can make use of passive energy sources. That means naturally existing energy can be also tapped. That, for example, adjacent to a major highway, lot of vehicles, cars, bikes as well as trucks are moving. The signals or noise created by them itself can be continuously sensed by us. Right? This is how we energize the subsurface. Then coming to the receivers. Receivers are the same. That means if we are carrying out MASWA, we can use vertical component geophones. Right? That the same vertical component was used for seismic refraction survey also. In reflection, horizontal component is usually used. In refraction, we use vertical component geophone. Right. So, the same geophone can be used. I showed a picture when we were looking into seismic operation on land. So, this is a picture of a geophone taken by me during the survey carried out. So, to give you an idea, I have put my pen adjacent to that. So, the total length of the geophone is almost equivalent to that of a pen. Half of it goes for the spike. So, the actual geophone is only of about 2-3 inches length of my index finger. Right. So, this is a vertical component geophone. Here you can see these are all the geophones. Right. The geophones which we use in seismic surface wave method, which is multi-channel analysis of surface waves, are usually low frequency geophones. Right. Low frequency geophones are used in MASWA. As we had seen already, short wavelengths are very close to the surface. Long wavelength signals are from deeper parts of the subsurface, deeper in the sense 30-40 meters. Right. So, this is how the receivers used in multi-channel analysis is the same as that of what we had used in seismic refraction survey. So, we have seen what are all the sources and what are all the receivers. Now, let us see how we are going to carry out the method on the surface of the earth. The way in which we carry out the survey on the earth is also almost similar to that of seismic refraction and reflection method. Right. Here is the source and this is the offset, first offset. After that, we arrange the geophones at more or less the same distance, maybe 1 meter or 2 meters or 3 meters. This is how the geophones are arranged at the surface, and the geophones are connected to a seismograph and the data is collected. So, we energize the ground, we give one hammer blow and all these geophones receives the Rayleigh waves, right, and the signals received are recorded by a seismograph. After that, there are some additional techniques which we are going to use. One is we need to analyze the multi-channel data we have received, right, to arrive at what is known as how the waves are getting dispersed. We prepare what is known as dispersion curve is arrived at for each and every shot. For every time whenever we energize the ground, we arrive at one dispersion curve. What is dispersion curve? Dispersion curve gives a relation between the velocity and the wavelength, right. So, we are getting a relationship between velocity and wavelength. So, that is what we see here. After arriving at that, we come out with a cross section of the subsurface which shows depth, distance, and what you see inside is the variation in the velocity of the formation, variation in the seismic velocity of different formations. So, this is in brief about the method. So, more or less the field operation is more or less the same, data processing alone is different, right. And as you can see, first we are having one short point here, similar to seismic reflection. Here also only one sounding is not sufficient, right. We actually move along a profile, right. This is first, this is second sounding, third can be somewhere here, this will become the short point. Hammer blow is given here, these are all the geophones, right. This is number 1, 2, 3. So, this is how we may progress along a line. This will become a short point. This is the hammer blow. These are the receivers, right. So, we plan a particular method of investigation, right. There are also lot of variation, right. Instead of this, we can also energize from the center. This is the location at which we can energize hammer blow. That means the receivers are kept symmetrically on either side, right. Or you can give one hammer blow, analyze the data, and source alone can be shifted to the other side. Here you can give a hammer blow. So, we need to plan a particular method of arrangement of geophones and short points. After that, we are going to energize, we give a hammer blow and acquire the data in multi-channels, right, which are known as short gathers. After having obtained the data, we will do dispersion analysis. So, dispersion analysis is nothing but extraction of dispersion curves, right. So, dispersion curves are, as I told you previously, right, either it relates velocity with the wavelength or here frequency with the velocity, all the same, because we had seen the relation between already wavelength lambda. What is the relation between wavelength, amplitude as well as velocity, right. We have seen already, right. What is the relationship between the velocity, frequency and wavelength we have seen. So, you need to plot a relationship between velocity and frequency, which is what is known as dispersion analysis. After having arrived at that, then we go for inversion. So, the procedure of inversion is exactly same as that of what we had seen under electrical resistivity method, magnetic method and gravity method. So, what we are doing here is, now we have got a dispersion curve after conducting a survey in the field. Now, in order to arrive at this dispersion curves, what is the likely subsurface formations, right. That means we assign some properties, some rocks below the surface of the earth for which properties are assigned. For the assigned or assumed subsurface conditions, we theoretically calculate the dispersion curves, right? How did we got this dispersion curve? By conducting the field survey. Now, without conducting the field survey, we assume certain subsurface geological conditions and their parameters for such a formation. What is the likely dispersion curve we will get? That process is known as inversion. We will get one inversion curve, right? Imagine this is the dispersion analysis obtained for a imagined earth model number 1. We got some pattern here. We compare both. When you compare, if both are reasonably matching, you continue. We say okay. If they are not matching, go for model 2. That means you change the assumptions little bit and work out a dispersion curve. Compare with this. So, this is how we do a process of trial and error with a condition, right? You cannot be indefinitely conducting this. You may say, when the comparison between what I had obtained by my computer modeling and what I got from the field, if they are matching nearly by, let us say, by 95%, then I will say okay. After that, you arrive at what is known as a two-dimensional cross section of the subsurface is obtained, right? You can either get 2D, and from 2D you can interpret 1D, or we can, suppose if the survey is conducted in several sections, right? What you see here is only I am showing how we have moved along one profile. Suppose, imagine this is the steady site. We have moved along this profile. I have the cross section here. This is profile number 1, then number 2, 3, 4. Right? That means we have got cross sections at number of profiles. That means I can convert this into a 3D diagram, because I can also interpolate what is between this profile and this profile by simple interpolation or by any other interpolating technique. So, by at the end I have what is known as the cross section of the subsurface. What cross section? This cross section is different from that of what we got under seismic reflection method. Here we get the velocity profile, right? The shear wave velocity profile we could obtain by inversion technique, right? That means if you have such a velocity distribution below the surface, only then you would have got such a surface wave dispersion curve. Okay. So, this is in simple about the multi-channel analysis of surface waves. That means the operation is exactly similar to that of what we did under seismic refraction and reflection method, but subsequently after that, since we are making use of surface waves, Rayleigh waves, which are dispersing type of waves, so we prepare what is known as, we conduct dispersion analysis, which is new here. Then we do inversion. Inversion we have done also in all the other methods. So, dispersion analysis is something unique for multi-channel analysis of surface waves. After conducting dispersion analysis, we back calculate the shear velocity, right? We assume certain subsurface conditions, some velocity distribution, then we arrive at what we got from the field. We try to match. So, this is how, and we finally arrive at the, what we arrive at? We arrive at the shear wave velocity distribution below the surface of the earth.